Hello everyone, this is Dr. Abdul Pasha, Assistant Professor, Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are in the course of Power System Operation and Control. So in this we are going to discuss about numerical analysis on fuel costs and generation limits. Earlier we discussed about cost curve analysis, which will be considered from input-output characteristics when it is undergone thermal schedule processing. Now here, when we go for numerical analysis of fuel costs and generation limits, these are better explained with 2 units or more than that. So here is a simple problem that will analyze us how we can make a numerical analysis on fuel costs and generation limits. So coming to this, the problem is like this. Consider 2 generating plants with the same fuel costs and generation limits. They are supposed to be given by Fi equals to 0.8 by 2 pi square plus 10 pi plus 25 rupees per hour, where I parameters are starting from 1, 2. Their power rating is in the range of 100 megawatts less than or equals to pi less than or equals to 500 megawatts, where I equals to 1, 2. So for a particular time of a year, the load in a day varies as which will be shown. So an additional cost of 5,000 is incurred by switching of a unit during the off-peak hours and switching it back on during the peak hours. So we have to calculate whether it is economical to have both units operational all the time. That we need to calculate here. Now coming to this, whatever the diagram we discussed here, that is for a particular time of year, total load in a day, that should be varies like this. So this may be simply treated as hourly distribution of a load for the units. So that means this is considered in between the load versus time of the day. The time of the day is considered in hours. Time of the day is considered in hours. So that means the curve is drawn in between load versus time. Load versus. So here the curve will start from this point and it will move like this. Again it continues to further, and like this will happens to continue for the given particular load. For example, the load consumptions from 200, 600, 1000, like that, so on. The load will takes place like this. So here time of the day. Time of the day means that may considered in hours. So the time factor may be 9, 18, 6, like that. It may follows for the given particular period of time how the load will be considered. That will be given here. So since both the units have identical fuel costs, we can switch off any one of the 2 units. The thing is that if the units have identical fuel costs, that means same rating, same cost. So we have to switch off any one of the 2 units during the off-peak hours. During a not requirement case, that means we can switch off any one of the 2 units. So therefore the cost of running of 1 unit from midnight to 9 in the morning while delivering load about 200 megawatts is, that may be treated as So here it is already given with Fi, that is 0.8 by 2 pi square plus 10 pi plus 25 rupees per hour. So here load consumption is considered during the delivering period, that is about 200. So in the given expression, if you substitute this value at the place of pi case, if you substitute this 200 as pi, then we may say that this may be 0.8 by 2 pi square. Pi square means this will be 200 square plus 10 pi. So 10 pi means 10 into pi means 200 plus what is the given cost? 25 rupees per hour. So here 25 rupees per hour. So with this, when you calculate, then it becomes 25 here into, and it will be multiplied with 9. So this will gives the solution about 1,62,225 rupees. This we obtained. So this is the cost of running of one unit from midnight to 9. So that's why we are multiplying here 9 in the morning while delivering load about 200 megawatts. So that is 1,62,225 rupees. So this much is happened. Now adding the cost of 5,000 for decommissioning and commissioning the other unit after 9 hours. The total cost becomes 1,67,225. That means whatever you got 1,62,225, for this you just add 5,000 rupees. So this is because of the reason for decommissioning and commissioning purposes. So the other unit after this 9 hours period, the total cost becomes 1,67,225. So this is because of adding 5,000 rupees as a charges. On the other hand, what happens means, if both the units operates all through the off-peak hours, all the units operate all through the off-peak hours, starting, that means sharing the power equally, then we get a total cost of this much. That means 0.8 by 2, here pi is 200 square plus 10 into again pi plus 25, that is 9 equals to 1,62,225, and which will be added with 5,000, which is about 1,67,225 rupees. So that means here adding the cost of 5,000 significantly, which will be for 2, means here running for 2 units, the cost may be 90,450. So coming to here, another numerical analysis is given. The fuel inputs per hour of plants 1 and 2 are given as determine the economic operating schedule and the corresponding cost of generation if the maximum and minimum loading on each unit is 100 megawatts and 25 megawatts. The demand is 180 megawatts. Demand is 180 megawatts. Transmission losses are here neglected. We are neglecting the transmission losses. The load is equally shared. So we are making an equal sharing of the load by both the units to determine the savings obtained by the loading the units as per equal incremental production cost. So their equal incremental production costs are mentioned here as F1, F2, where F1 is 0.2 P1 square plus 40 P1 plus 120 rupees per hour. Next F2 is 0.25 P2 square plus 30 P2 plus 150 rupees per hour. So incremental production costs of both the units are represented in dF1 by dP1, where increment is represented with a change, that is D. So then df1 by dp1 equals to, so when you make this one, then if you consider this differentiation coefficient, this p square coefficient becomes 2 into 0.2. So here 2 into 0.2, that is about 0.4. So here straight away P1 becomes 1. P1 becomes 1 means here 1. That is directly 40 rupees per megawatt hour. And here coming to here df2 by dp2, where here 120 value becomes 0. Why? Because we are making d by this coefficient, incremental representation. During the differential cases, this differentiation of 120 will leads to 0. That's why we have left over with these parameters 0.2 p1 square plus 40 p1, where this value becomes 0. So 2 into 0.2, that means 0.4. Here straight away p1 becomes 1. Then straight away 40 into 1, 40. So this is the expression we got for the unit 1, df1 by dp1. So that is 0.4 p1 plus 40 rupees per megawatt hour. Similarly, df2 by dp2 is equals to 0.5 p2 plus 30 rupees per megawatt. That means here 2 is multiplied with 0.25, then 0.25 into 2. That is about 0.5. Similarly, here P2 becomes 1. So P2 becomes 1 means 30 into 1, 30 rupees per megawatt hour. So this is the incremental production cost. Now for economic operation of multi-units, we must equate their coefficient. That is df1 by dp1 is equals to df2 by dp2. So this we must equate. This is because of economic operation of the two units considered together. So what about df1 by dp1 value? So that we already derived here 0.4 p1 plus 40 rupees per megawatt. So that we need to write 0.4 p1 plus 40. Similarly, 0.5 p2 plus 30 gives about df2 by dp2. 0.5 p2 plus 30. Now equating these two, 0.4 p1 plus 40 is equals to 0.5 p2 plus 30. When you equate these two, then what you obtained is here 0.4 p1 plus 40 minus 0.5 p2. So like this you may get. So 0.4 p1 plus 40 minus 0.5 p2 minus 30 equals to 0. So that means what happens to here to the coefficients means the summation of the coefficients of p1 plus p2 you may obtain with a value of 180. If you simplify this one, then you may get 180. P1 plus P2 value is about 180. So solution of these equations gives individual. When you make individual equation solutions, then you get P1 is 88.89 megawatts, P2 is 91.11 megawatts. So now cost of generation is F1 plus F2, both are F1 plus F2. So F1 equals to 0.2 P1 square plus 40 P1 plus 120. We already have this one, 0.2 P1 square plus 40 P1 plus 120. So here instead of P1, you substitute this 88 value. So instead of P1 substituting, here also there, the same value, 88.89 megawatts. So here it becomes a square term. That is 88.89 square term here. And this is straight away 40 into 88.89. Finally, if it is added to 120 means you may obtain a value of 5,255.88 rupees per hour. So this you may obtain. Similarly, if you do the process for F2, second unit, that is 0.25 P2 square plus 30 P2 plus 150. So here also substitute P2 value. What is P2 value? 91.11. So 91.11 whole square plus P2 value again 91.11. 30 into 91.11 plus 150, which gives 4,958.55 rupees per hour. This you may update. Now total cost is summation of these two. That is this 5,255.88 plus 4,958.55. So if you equate these two, then you may obtain 10,214.43 rupees per hour. This is the total cost incurred. If the load on each unit is 90 megawatts, now the assumption is that the load is on particular unit is 90 megawatts, the cost of generation will be. So how the cost of generation? F1 is 5,340 rupees per hour. F2 is 4,875 rupees per hour. Like that we may obtain F1, F2 values. Now, when you make this total cost, you may obtain a value of 10,215 rupees per hour. So, how much saving is obtained with this means there will be about 0.57 rupees per hour. How can we obtain this one? Now you subtract this one, 10,215 minus 10,240, which are in points 4, 3. This is which are in about 10,214, and this is about 4, 3. This is about straight away 10,215. That means you are getting a final savings about 0.57 rupees per hour. This is the amount we may save with these total costs. Next, the fuel cost of 2 units are given here with the C1 and C2. C1 is of PG1, C2 is of PG2. That is 1.0 plus 25 PG1 plus 0.2 PG1 square in rupees per hour. And C2 is C2 of PG2, 1.5 plus 35 PG2 plus 0.2 PG2 square in rupees per hour. If the total demand on the generator is 200 megawatts, total demand on the generator is 200 megawatts, find the economic load scheduling of the 2 units. So how can we calculate? Means we should have one condition. The condition for economic load scheduling when neglecting the transmission losses are DCI by DPGI equals to lambda. This is one of the Lagrange's coefficient. So for I equals to 1, 2, 3 up to so on, and it will take place. So that is DC1 by DPG1 is equals to DC2 by DPG2 is equals to DC3 by DPG3. Like that so on, we can extend our analysis up to DCN by DPG, which is equals to lambda. So we can extend till this. So here costs are given, fuel costs C1, C2, where C1 is 1 plus 25 PG1 plus 0.12 PG1 square. C2 is 1.5 plus 35 PG2 plus 0.12 PG2 square. So with these two costs, if you apply the concept of this one, DC1 by DPG1, so this becomes calculated or simplified here. Your 1 becomes 0 when you make DC1 by DPG1, and this becomes straight away 25, and this becomes with respect to PG1 na, so this becomes 1. So 25 plus this 0.12 PG1 square becomes 2 into 0.12, that is 2 into 0.12 means 0.4. So 0.4 PG1 in rupees per megawatt hour. Similarly, DC2 by DPG2. So 1.5 is 0. So this 35 PG2 is, if PG2 is 1, you are left over with only 35, and 0.12 PG2 square becomes 2 into 0.12. That means 0.4 PG2. So these are the two expressions you obtain when you make the differentiation of these two expressions. Whatever the expressions we have here, when you make with respect to the condition of economic load scheduling when neglecting the transmission losses. So with this you obtain these two conditions. So DC1 by DPG1 is equals to 25 plus 0.4 PG1, and DC2 by DPG2 equals to 35 plus 0.4 PG2. So with these two equations and conditions, when you apply economical load dispatch, to make economical load dispatch, we must equate these two coefficients. DC1 by DPG1 is equals to DC2 by DPG2, which is equals to lambda. So what is the value of DC1 by DPG1? 25 plus 0.4 PG1. What is DC2 by DPG2? 35 plus 0.4 PG2. This we already calculated. And we may write this one as 0.4 PG1 minus 0.4 PG2. So we are bringing these two to a LHS side and making these two coefficient onto the RHS side. That means 35 minus 25, which gives about 10 megawatts. So 0.4 PG1 minus 0.4 PG2 is equals to 10 megawatts. Now equate these two, that means PG1 plus PG2, this sum is equals to 200 megawatts. When you simplify this expression, finally you are getting 200 megawatts. By solving these equations, whatever we got, so, and one more thing we need to add here is multiplying both sides of equation by 0.4. Here on both sides you multiply with 0.4. Why? Because here 0.4 is common for on both sides. That's why we need to multiply. Then 0.4 PG1 plus 0.4 PG2 is equals to 0.4 into 200. That is about 80. So by adding equations, then we may obtain 0.8 PG1 equals to 90. This is happen in terms of PG1. So PG1 equals to 90 by 0.8. That is 112.5 megawatts. This is the value of first PG1. And if you obtain PG1 value about 112.5 megawatts, substitute this, then in the equation, then it becomes PG1 is 112.5 plus PG2 here itself if you substitute. So instead of PG1, 112.5 plus PG2 equals to 200. So in this equation, then PG2 you may obtain, that is 87.5 megawatts. You can cross check this first PG1 value 112.5 plus second obtained value 87.5. Then these two cumulatively gives 200 megawatts. So this is the first value and this is the second value, PG1 and PG2. Now another case is about 3 power plants of total capacity 500 megawatts which are scheduled for operation to supply total system load of 350 megawatts. Find the optimum scheduling if plants have incremental cost characteristics. That means DC1 by DP1 equals to 40 plus 0.25 P1, which is ranging from 30 to 150. That is 30 less than or equals to P1 less than or equals to 150. Similarly, DC2 by DP2, which is equals to 50 plus 0.3 P2, 40 less than or equals to PT less than or equals to 120. Similarly, DC3 by DP3, 20 plus 0.2 P3, which is about 50 less than or equals to P3 less than or equals to 225. So with these three conditions, we need to make the solution, right? So for economic load scheduling among the power plants, the necessary condition dCi by dPgi equals to lambda. So for three plants, we must equate these conditions. dC1 by dPg1 is equals to dC2 by dPg2, which is equals to dC3 by dPg3. All are equal to the coefficient lambda. So what is the given total load? Pg1 plus Pg2 plus Pg3 equals to 350 megawatts. So how can we see this means? Here it is already given that which are scheduled for operation of supply total system load of 350 megawatts. So that's 350 megawatts we written here. And if you consider this one with the first case, that is 40 plus 0.25 Pg1, and the second one is 50 plus 0.30 Pg2, and which is equals to third one 20 plus 0.2 Pg3, which is all are equivalent to lambda. So what happens here means we should equate the first coefficient with the second coefficient, means dCi by dPgi equals dC2 by dPg2 equals to 40 plus 0.25 Pg1 equals 50 plus 0.30 Pg2. So what happens with this? You just simplify this one and remove this equal and make it to minus 50 minus 0.30 Pg2. When you equate to this, 40 plus 0.25 Pg1 is equals to 20 plus 0.2 Pg3. So, or we may write this expression again as 0.25 Pgy minus 0.2 Pg3 equals to 20 minus 40, which is about minus 20. So, with this 0.25 Pgi minus 10 equals to 0.30 Pg2, where Pg2 is 0.25 Pg1 minus 10 by 0.3, which is equals to 0.833 Pg1 minus 33.33. So Pg1 plus 0.833 Pg1 minus 33.33 plus Pg3 equals to 350. Or we may represent this as 1.833 Pg1 plus Pg2 equals to 383.33. So 0.25 Pg1 minus 0.2 Pg2 equals to minus 20. And 0.366 Pg2 plus 0.2 Pg2 equals to 76.66. So when you simplify these two conditions, 0.616 Pg1 equals to 56.66. Or we may get this value Pg1 equals to 91.98 megawatts. So substituting the value of Pg1, then you may get 1.833 into 91.98 plus Pg3 equals to 383.33, or Pg3 equals to 214.73 megawatts. Now substituting the values of these Pg1 and Pg2 in the above expressions, then 91.98 plus Pg2 plus 214.73 equals to 350. So with this you may get the second Pg, so 43.29 megawatts. Next case is the incremental fuel cost for two plants are the loss coefficients, which are given as B11 equals to 0.0015 per megawatt. B12 is B21 equals to minus 0.0004 megawatt, and B22 equals 0.0032 per megawatt. For lambda equals to 25 rupees per megawatt. Find the real power generations, total load demand, and the transmission power. So here are the expressions given for two units. dC1 by dPg1 is 0.075 Pg1 plus 18, which are in rupees per megawatt hour. dC2 by dPg2 equals to 0.08 plus Eg2 plus 16 in rupees per megawatt hour. So now equate these, Pg1 plus Pg2 equals to Pd plus PL. This is the total load demand, and the transmission loss is PL equals to summation P equals to 1 to N, Q equals to 1 to N, Pg1, PPQ, PGQ. So for number of plants N equals to 2, we have PL equals to summation P equals to 1 to 2, Q equals to 1 to 2, PGP, BPQ, PGQ. So with these conditions, if you simplify, Pg1 B11 Pg1 plus Pg1 B12 Pg2, Pg2 B21 Pg1 plus Pg2 B22 Pg2. Now substitute these conditions. Then with the given values, my 0.0015 Pg1 square, 2 into minus 0.0004 Pg1 Pg2 plus 0.0032 Pg2 square, which are equal to 0.0015 Pg1 square minus 0.008 Pg1 Pg2 plus 0.0032 Pg2 square. So the incremental cost of the plant 1 is, that is ITL dou PL by dou Pg1, 2 into 0.0015 Pgi minus 0.008 Pg2. So here penalty factor of that particular plant 1 is L1, that is 1 by 1 minus dou PL by dou Pg1. When you substitute these values here, then you may get 1 minus 0.003 Pg1 minus 0.0008 Pg2. So similarly, for the plant 2, ITL of 2 is dou PL by dou Pg2 minus 0.008 Pg1 plus 0.0064. And the penalty factor for the same plant 2 is L2, that is 1 by 1 minus dou PL by dou Pg2. Substitute these conditions. 1 minus 0.008 Pg1 plus 0.0064 Pg2. Now condition for optimum generation is dou C1 by dou Pg1 L1 equals to dou C2 by dou Pg2 L2 equals to lambda. So dou C1 by dou Pg1 L1 is lambda. Substituting these conditions here, 0.075 Pg1 plus 18 into 1 by 1 minus 0.003 Pg1 minus 0.008 Pg2, which is about 25. So equating all these values, 0.0075 Pg1 plus 18 is equals to 25 into 1 minus 0.003 Pg1 minus 0.008 Pg2. Or we may write this condition as 0.15 Pg1 minus 0.02 Pg2 equals to about 7. So again, if you equate this dou C2 by dou Pg2 L2 to the lambda, then multiplying this coefficient 0.08 Pg2 plus 16 into 1 by 1 minus minus of 0.008 Pg1 plus 0.006 Pg2 gives 25. So if you simplify this condition, you may get 0.002 Pg1 minus 0.24 Pg2, which is about minus 3. Now solving for the expressions, you may obtain Pg1 52.247 megawatts. Now substituting this Pg1, then 0.15 52.247 minus 0.02 Pg2, which is equal to 7. So therefore Pg2 value is 41.852 megawatts. Now transmission loss coefficient is PL, that is 0.0015 into 52.247 whole square minus 0.0008 52.247 into 41.852 plus 0.0032 41.852 whole square. Finally, you may obtain transmission loss as 7.95 megawatts. Now with this total load can be calculated as PD, that is Pg1 plus Pg2 minus PL, that is 52.247 plus 41.85 minus 7.95, that is 86.149 megawatts. So this is the solution we will obtain. So these are the some references which I have considered from the web sources and video lectures and some textbooks. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.